Today, we're going to dive into a really fascinating, powerful idea that's been making some serious waves in the world of AI. It's called deep active inference, and it's this amazing framework that tries to bring learning, perception, and action all together under one single elegant rule.
So think about this for a second. What if you could build an intelligent agent, a robot, a piece of software, whatever, that runs on just one fundamental driving force? Not some complicated web of rewards and punishments, but just a single, simple rule that could explain all of its behavior. Well, that is the core promise of active inference.
And that one simple rule, it's all about minimizing surprise. Seriously, that's it. This is the absolute bedrock of the entire theory, the foundation everything else is built on.
At the very heart of this is something called the free energy principle. Now I know, the name comes from physics and sounds a little intimidating, but the idea is actually super intuitive. It just says that any adaptive agent, from a single cell to a human brain to a sophisticated robot, is constantly working to make its world predictable. It acts to avoid being surprised by what it sees, hears, and feels.
To make this feel a bit more real, let's imagine a curious robot detective. Now, its main mission isn't just to solve the case. Its real goal is to constantly update its theory of the case so that no new clue, no piece of evidence ever comes as a shock. Every single action it takes is designed to either confirm what it already expects or to gather new information that makes the world less surprising down the road.
Okay, so how does our detective actually do this? This is where perception, which is just understanding the world, and action, doing stuff in it, come together in this really powerful feedback loop. First off, the agent needs some kind of internal model of how the world works. In the lingo, this is called a generative model. For our detective, this is basically its theory of the case. It's this internal story it's telling itself, and it uses that story to generate predictions about what it expects to see next. And this leads to this core cycle that's always running. The agent uses its model to predict what it's about to see, then it actually looks at the world. Now, if there's a mismatch, a surprise, it first updates its beliefs. That's perception. But, and here's the magic part, it can also act on the world to make its predictions actually come true, which actively cuts down on future surprise. This is how it ties perception and action together under one single goal.
So how does the agent decide what to do? Well, it's constantly balancing two competing drives. On one hand, you've got the epistemic drive. That's just pure curiosity, the detective wanting to go out and gather more clues just to reduce its uncertainty. But on the other hand, it has a pragmatic drive, the desire to get to states it prefers, or in our analogy, to actually solve the case. It's this constant dance between exploring to learn new things and exploiting what it already knows to get things done.
Now, this theory has actually been around for a while, but it got totally supercharged recently by this incredibly powerful tool from modern AI, deep learning. Let's see how adding the deep completely changes the game.
See, the classical active inference models, they were fantastic in theory, but they kind of struggled with the messiness of the real world. Things like raw video footage or complicated audio. But deep neural networks, they just blow the doors wide open. They can handle all of that complex, high-dimensional stuff, allowing these agents to build these incredible generative models for pretty much any environment you can throw at them.
And hey, for those of you who are already familiar with machine learning, this is where you might have a big aha moment. The way deep active inference actually works under the hood is incredibly similar to a really popular type of neural network, the variational autoencoder, or VAE.
So you can think of it like this. The agent's perception is kind of like an encoder. It takes in all this complicated sensory data, like a photo, and it squishes it down into a simple set of beliefs. And then the generative model acts like a decoder. It takes those simple beliefs and tries to recreate or predict the original photo. The agent learns by constantly trying to make its decoded prediction a perfect match for the real thing, which is just another way of saying minimizing surprise.
This whole framework is so powerful that it's not really just one single algorithm, it's more like a whole family of them. Researchers are exploring all these different ways to implement this core idea, and we can kind of group them into a few main flavors.
So yeah, this isn't just one recipe, it's a whole cookbook. You've got different teams taking different approaches to bring this theory to life. Some are connecting it to ideas we're already familiar with, like reinforcement learning. Others are focusing on building these massive, deep world models that let an agent plan far into the future. The key thing to know here is that this is a super active and diverse field of research.
So what does all this mean? Why are so many researchers getting so excited about this? Well, it's because deep active inference promises to be way more than just another AI algorithm. This is the key right here. Deep active inference gives us a single, cohesive framework that's grounded in solid theoretical principles, specifically Bayesian inference, that could potentially explain both learning and control. It's this incredible bridge between how we build artificial agents and our theories about how biological brains, like our own, might actually work. It's a potential theory of everything for intelligence.
So if you only take away 3 things from all this, let it be these. First, intelligence can be framed very elegantly as just a process of minimizing surprise. Second, intelligent agents are always doing this balancing act between needing to learn more about their world and needing to achieve their goals. And third, modern deep learning is the magic ingredient that takes this beautiful theory and makes it a practical reality for solving really complex problems.
And that leaves us with this one final, kind of mind-blowing thought to chew on. If all adaptive living systems are just trying to minimize surprise, could this one single idea explain intelligence at every single scale, from a single cell reacting to chemicals in its environment, all the way up to the incredible complexities of human consciousness? That's a pretty big question to ponder. Thanks for joining us for this explainer.